Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. Ant. In this tutorial video, we'll go through this AQA chemistry. This is a topical series. This is about shape of molecules. So basically shape of molecule follows this VSEPR, VESPR, which stands for valence shell, outermost shell, electron pair repulsion theory. So for instance, we have these questions on ammonia as well as aluminium trichloride to give us this particular compound here. So what we're going to do, draw diagrams to illustrate the shape, to show the shape, to demonstrate the shape of NH3 molecule, AlCO3 molecules. And we're going to think about nitrogen with 5 electrons in the outer shells that form single covalent bond to each of the hydrogens. You only count the sigma covalent bonds. In a single bond setting, there has to be a sigma, sigma, and sigma. So you have 3 sigma covalent bond. So that is what you call 3 bond pairs. So nitrogen has 5 outer shell electrons from your IGCSE or A Level chemistry. With the 5 electrons in the outer shell, you share 1, 2, and 3 out of 5. You still have 2 more electrons left on each nitrogen. That is called non-bonding pair or lone pair of electrons. In terms of VSEPR, it basically says that when you have a lone pair, so we can say that the lone pair and the lone pair, there's only one lone pair actually. So the lone pair and the bond pair, they repel more. They repels more than the bond pair, and as a result of that you are going to get a pyramidal geometry, a pyramidal or a trigonal pyramidal geometry. So trigonal pyramidal, or you can call it pyramidal. This is going to be slightly smaller than the tetrahedral. This is 107 degree. Draw or indicate the values of the bond angles on the diagram. Indicate on your diagram any lone pairs of electrons. I just did that. I explained that. And this is 3 marks for 2 parts of the question. The second part is on the aluminium trichloride. Aluminium with 3 electrons in the outer shell, chlorine 7 electrons in the outer shell. You would imagine that for aluminium trichloride, you would think about metal and non-metal, you think about ionic, but the very reason they have talked to you about this word called molecule, the word molecule there means is covalent rather than ionic. So what I can do is really aluminium, chlorine, chlorine, and chlorine. The reason I draw it like that is because after you use 3 out of 3 outer shell electrons for bonding, you are just left with 3 bond pairs. Those are your sigma covalent bond. And then you're left with 0 lone pairs because there is no more electron left on the aluminium center. So what we can say is the 3 bond pairs will repel equally because there is no lone pair. So they repel equally. So what shape you get will be a trigonal planar. Look a little bit like the Mercedes-Benz logo. There's going to be 360 degree divided by 3 because this is a totally flat structure. There's 120 degree there, 120 degree there, as well as 120 degree there. Part B, name the type of bond, name it, between the nitrogen and aluminium in this complex, and explain how this bond is formed. If you imagine just now where you have the ammonia molecule, like that in 3-dimensional. So that is your pyramidal. So that was 107 degree in this pyramidal geometry. So you have aluminium trichloride. So there was 120 degree trigonal planar. If you look around the aluminium only has 6 electrons in the outer shell, 2, 4, and 6. We know that usually you can fit up to 18 electrons for the 3rd period chemistry, for which aluminium is a 3rd period element. So what's going to happen with this nitrogen? Let me just draw this, is that it's going to use its lone pair of electrons and it's going to donate these to the empty orbitals for the aluminium. So I should probably use back the blue color one. And then the aluminium has gone from 3 sigma covalent bond, 3 bond pair, to having the original 3 plus 1 more from the nitrogen. So now the aluminium is also going to become tetrahedral. So this nitrogen now has got 1, 2, 3, and 4 bond pair, 0 lone pair. On the aluminium, you got 1, 2, 3, 4. This is a single covalent bond. So there has got to be a sigma covalent bond, 0 lone pair. So both of them are going now to be tetrahedral, 109.5 degree or 109 degree there. So both nitrogen and aluminium has become tetrahedral. So the type of bond is a very special type of covalent bond. You call it dative covalent bond. The other name of which would be in your syllabus is called coordinate bonding. So coordinate bonding simply means dative covalent bond. It means that both the electrons in the covalent bond come from only one of the atom forming the covalent bond. Because here, instead of the aluminum sharing one electron here, is the nitrogen that contribute both the electrons. That's why we have this arrow to indicate or to tell us that this is the donor of two electrons going to the empty orbitals. The aluminum is accepting the pair of electrons there. So in terms of the explanation, so the nitrogen uses its lone pair of electron to donate both the electrons, for the covalent bond, for covalent bonding to the empty orbitals. So you must have empty orbital that can accept the two electrons on the aluminium of AlCl3 molecule for that 2 marks there. In part C, so explain how the value of the Cl-Al Cl bond angle changes, if at all, in forming that compound. So I just did earlier, we already explained the 120 degree earlier. So 120 degree trigonal planar geometry in the original AlCl3 now becomes 109.5 because this is now tetrahedral aluminium in the resulting compound, which is that thing there, which I could potentially just show this diagram because now you have 4 bond pair and 0 lone pair. So if I just show that diagram there, so now aluminium has, explain how the value changes. Okay, that's probably not a, in hindsight, that's probably not a good thing to copy there. So this is due to around the aluminium. Now we have 4 covalent bonds, the original 3 covalent bonds plus 1 more dative covalent bond. So we have 4 sigma covalent bonds. So therefore 4 bond pairs, 0 lone pairs. So this is about shape of molecule again. So 4 bond pair repel equally, and the 4 bond pair repel equally to give you a tetrahedral geometry. A tetrahedral geometry will be 109.5 degree on each of the aluminium center there. And that's it for that 7 marks first question. I'm going to skip, no, I think I should do this second question actually. Write any question including stat symbols. This is about enthalpy change. You will probably learn more about this if you haven't. This is in the AQA syllabus under energetics. Usually by the topic on structure and bonding and share molecule, you wouldn't have covered this. But if you had, then you know. It's about the enthalpy change when you form 1 mole of the substance. So the stat symbols are very important from its elements. So carbon as an element could be diamond or could be graphite, but it will have a giant covalent structure from your IGCSE chemistry or A Level chemistry. There will be a solid there. And then I'm reacting with this diatomic element, group 7 halogen molecule. And then I'll need to balance the equation. Cannot change the number here, has to be for forming 1 mole of the substance from its elements in standard states, everything under standard conditions for that 1 mark there. But the actual essence of this particular tutorial, the focus will have been on the bond angles, the shape of molecule. So this is about CF4, carbon with 4 electrons in the outer shell, wants to share 4 electrons to complete the outer shell. So they will form 4 covalent bond because they want to share 4 electrons in the outer shells to complete the outer shell. Fluorine to 7, so you have got 7 electrons in the outer shell. Therefore, you want to form 1 covalent bond to complete your outer shell, which is the second shell right now. So when I draw this molecule, I will have a single bond between fluorine and carbon because the fluorine share 1 electron, the carbon share 1 electron. But the carbon wants to form 4 covalent bonds, so I got 4 of them. I haven't drawn three-dimensional yet, but what I can do is I can draw the display formula where I draw the bond as line, and each of that single line is a single covalent bond. So I can say is around the carbon, around the central carbon. So what I have there is there are 4 bond pairs because you count the sigma covalent bond. 1, 2, 3, 4 sigma single covalent bond, and then 0 lone pair because carbon has 4 electrons in the outer shell. You share 1, 2, 3, and 4. You have none left in the outer shells. So therefore, the 4 bond pair repel equally. If the 4 bond pair repels equally, so you're gonna get not a 2-dimensional structure, but a 3-dimensional structure where you call this tetrahedral. Tetrahedral is a 3-dimensional structure where the bond angle is not 90 degrees because they are not as far apart as 109.5 degrees, where I can actually draw the 3-dimensional structure like 2 of the flat line where these are about 109.5 degrees, and then this wedge is coming out, is pointing at you right in the eye, and then this dashed line is behind the screen, is going away from you behind the screen there. In part C, this is a little bit more on that topic on standard enthalpy of formation. So we know about when we have reactants going to products. So I'm just drawing a general Hess law diagram. You will learn more about this in that topic on energetics. So I'm forming the reactants. So that's called the formation, enthalpy of formation of the reactant. And then I'm forming the product. That's called the enthalpy of formation of the product. Hess's law says that enthalpy change of a reaction does not depend on which path you take. So I can come down to the elements and then go up to the product. I'm going opposite that. So it's going to be minus the formation of reactant plus the formation of products. So if I have the enthalpy change of reaction for this reaction, it's going to be the sum or the total of the enthalpy of formation of product minus the sum of the enthalpy of formation of the reactant based on the general, Hess law or Hess diagram that I have on top there. So minus 2889 is the enthalpy change of reaction. I want to calculate the enthalpy of formation of C2H6. So the C2H6, the equation is already given here. This is element, enthalpy of formation of element from its element is going to be 0, hence they give you a 0 there. What do they want me to find? They want me to find the C2H6, so give that as X. I'm forming 2 mole of that. So the formation of product, so 2 times minus 6 at 0, because I'm forming 2 mole of the CF4. I'm forming 6 mole of the HF, so 6 times minus 269, close bracket. And I am having 1 mole of the reactant, so that's what I want to find X. So this is minus X, move the X to the other side. So minus 6 at 0 times 2, and then plus 6 times minus 269, I get minus 2974. I'm going to move this minus 2889 to the other side, become plus 2889. A little bit about bookkeeping, so make sure that 2899, and then I get minus 75 kilojoule per mole. Sign, value, and also unit for that 3 marks calculating standard enthalpy change of formation there. In part D, so this is a different reactions. Here they give you the mean bond enthalpy. So the mean bond enthalpy is basically, for example, CH there. You could have a CH in the methane or CH in the ethane. These are average over many molecules. So one reason for the high reactivity of fluorine is a weak fluorine-fluorine bond. So if it is easy to break, so that means that it's going to be quite reactive. If you see this question, they want you to calculate using this data. So find the energy of a FF bond. So I've started by talking about shape of molecule, but it seems like this particular question had a lot of focus on AS energetics kind of calculation. So if in terms of bond energy, we have to try and draw every single bond that we are forming and we are breaking. So there's your CH4, there's your FF, there are 4 of them, be careful. And then I'm forming the CF4, and this is a substitution reaction where I have substituted the hydrogen with fluorine instead of chlorine. Usually, typically, these are in the presence of UV light. So what we're going to do is, I'm going to form the gaseous atoms. So I'm going to get carbon, gaseous atom, hydrogen, gaseous atom, and then fluorine, gaseous atom. So this is going to go up as well. So that is going to be the bond energy broken minus the bond energy formed, as the Hess law says, starting from this point, ending at this point. The pathway doesn't matter because I could go up. The bond energy break everything in the reactant side, minus, because I'm going opposite to that. So the formula is actually going to be enthalpy change of reaction is the total energy for bond breaking minus the total energy for bond forming on the other side. So I already shown you that the bonds that we are forming as well as the bonds we are breaking. So we just need to do the correct multiple. Enthalpy change of reaction is given as minus 1904 kilojoule per mole. Bond breaking, we are breaking 4 of the CH. So 4 of the CH. We are breaking 4 times of the FF. So that is what we want to find. So 4 times X, that is going to be, let that energy of fluorine-fluorine bond be X, minus the energy for bond forming. I'm forming 4 times of the CF. So that's 4 times 484. And I'm forming 4 times HF covalent bond. So 4 times 562. So altogether, make X the subject. So let me just total this up first. So 4 times 412. So 1648 plus 4x minus 484 times 4 plus 4 times 562. That is minus 4184. So 4x is going to be minus 104 minus 1648 plus 4184. I should probably move this longer one to the other side. I mean, it's just mathematics, to be honest. Minus 1904 minus 1648 plus 4184. So that is going to be plus 632 divided by 4. And I get plus 158 kilojoule per mole. And that is the bond energy for the FF. This bond energy seems to be a bit low on compared to the other bonds. So is the student correct? Yes, pretty weak or relatively weak covalent bond. So it's quite easy to break, therefore it's quite reactive. Show your, justify your answer with a calculation, and I just did. Pretty weak bond energy there. That's it for that 10 marks question. Just to wrap up this particular tutorial, so which one has a trigonal planar structure? So trigonal planar structure has got 3 bond pairs repelling equally because you got 0 lone pairs. So therefore, the 3 bond pairs repel equally, giving you something that looks like the Mercedes-Benz logo. So you're looking for something with 3 bond pair and 0 lone pair. So phosphorus, after you form 3 covalent bond, phosphorus is in group 15 or group 5. It has got 5 outer shell electrons, 1, 2, 3. So they have 2 more. This is going to be pyramidal, 107 degree. Boron, just above aluminium, we know that this is going to be 120 degree because boron is in group 3, 3 outer shell electrons. Therefore, 3 bond pair and 0 lone pair. We have gotten the answer we are looking for, which is going to be option B there. In terms of H3O+, this is water. Water has got 2 bond pair and 2 lone pair. Originally, it will be 104.5 degree. This is called nonlinear, or you can call it bent or V-shaped geometry. In terms of dative covalent bond, what you can do is you can use one of the lone pair to form a dative covalent bond to the hydrogen ion, such that now you got 3 bond pair and 1 lone pair. So this is for the H3O+. Is what happens when you have acidic species. H3O+ is present as a result of H2O picking up H+. This is going to be pyramidal and 107 degree, just looking like ammonia molecule. CH3- is going to look exactly similar like that. When you think about it, there is a carbon, a hydrogen, and hydrogen. You will have 1 electron, but you have a -1, so really you have 1 more electrons, and therefore there's still going to be pyramidal 107 degree. Leaving you behind really B is the answer that you're looking for, not A, C, and D, because those are pyramidal, as well as pyramidal there. And that's it for these short tutorials. Started out with shell molecule, but it turns out that the middle question was more on AS energetics, which has to do with bond energy and enthalpy of formation. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. And do follow me at ptet.chemistry. That's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. So do let friends and chat groups, relatives, and juniors, seniors know about the various tutorial videos I have on my channel. And get in touch at 673, country code 8656158. Get in touch for private tutoring. We can go through any questions of your choice or review any topics of your choices. Thank you for watching again. I'll see you in the next tutorial video.